Welcome back, everyone. First, I want to play some clips from Physics 2 to cover more of the conceptual, less complex algebraic components of this unit. Then you're going to come back to me for the more calculus-heavy parts. And that brings us to our discussion of conductors, and you have insulators. I don't know how to spell insulators, but you get the idea. Okay? So, like I discussed previously, the positive charges inside any substance, any solid, let me be more specific, the positive charges in any solid will never move. The electrons, however, in a conductor are free to move. So we're talking about electrons here. The electrons in insulators are not free to move. If I had a conductor, like a big block of iron, and another conductor, like a big block of steel, and this one had a positive charge and this one had a negative charge, if I brought the two together and I touched them to each other, what do you think is going to happen? All the electrons from the negatively charged block will flow to the positively charged block because they're conductors and the electrons will freely move between them. Therefore, if I touch two charged conductors together, we're going to have a flow of electrons, and within a few milliseconds, or a few nanoseconds, more realistically, the two blocks will become neutral, and they will lose any charge they originally had. Let's reassume that this is an insulator, okay? And let's say that I were to bring a block of steel here, steel being a conductor. The electrons in a conductor are free to move about however they please. The positive charge on this rod, if I bring it closer to the steel brick, let me draw it so that you can see what I'm talking about. If I bring it much closer to the steel brick, the positive charges on the rod are going to attract the electrons within the conductor. So that means the electrons from throughout the conductor are going to be pulled towards this end, and they're going to be concentrated on this end. Okay? Which means there will be comparatively fewer electrons on the right. Recall that positive charges do not move. Positive charges can't move, okay? So if in the block there is now many more electrons on this side, that means there are many fewer electrons on this side. So if you have the same amount of positive protons with fewer electrons here, that means this side has developed a positive charge and this side has developed a negative charge, okay? However, this is a temporary charge arrangement, which means if I remove the glass rod, the charges will restabilize back into the neutral configuration of the brick. How do we give conductors a permanent charge? If I have my same positively charged glass rod and I were to have a conductor like this, I could connect this conductor to ground. This is the symbol for ground. Now, what is ground? Ground in this class is going to be defined as a place that is an infinite source and sink of electrons. What do those two words mean? An infinite source of electrons, I think that's pretty intuitive. You can pull as many electrons as you want from ground. A sink, an infinite sink of electrons, means you can donate as many electrons as you want to ground. In this example, I have a neutral conductor and a positively charged rod, and this positively charged rod is attracting electrons to the left side, okay? It's attracting the electrons in the brick to the left side, just the same as in the example before. However, the left side is developing a negative charge and the right side is now developing a positive charge, just like in the example before. However, now that the right side has developed a positive charge, it is attracting electrons from ground. So that means new electrons from ground are being pulled through the wire and they are coming into the block. So new electrons are coming in to replace all the electrons that left and moved to the left side. All right, such that this positive charge disappears, and I'm now left with just a negative charge concentrated near the positively charged rod, okay? So I have just a negative charge left on my block. If I remove the rod, all of the negative charge will flow back into ground and I'll be left with a neutrally charged brick. However, if I disconnect ground and then remove the rod, there will be no place for the negative charge on the block to go. Therefore, I'll be left with negatively charged brick. So main takeaways here is that in any conductor, there must be a zero electric field, okay? If the conductor has an excess of charge, the charge will become distributed throughout the surface of the conductor, such that if I were to look at the conductor's cross-section and let's say it had an excess negative charge would become concentrated on the surface of the conductor. So if I observed a particle in the center of the conductor, or at any point in the interior of the conductor, the net electric field inside the conductor would be zero. Again, because if there's an electric field, there would be movement of charge throughout the conductor, okay? Another thing we covered was the concept of ground, okay? Now, I just want to review this in detail because we're going to be covering circuits next unit, so it's important for us to understand the concept of ground. I'm going to be drawing a bunch of symbols that represent circuit components in our next video. So the symbol for ground is this. 3 descending lines like that. That's how you depict a ground connection when you're drawing a circuit, okay? So what precisely is ground? Well, as the name might entail, ground is like the ground of the earth, okay? The most effective ground would be connecting a conductor throughout a large surface below ground, okay? Like we know there's a bunch of sewer wires carrying water, like let's say throughout your town, okay? If you were to connect a conductor to that, that would be a very, very good ground. So what electrically is ground? Ground is what we call an infinite source and an infinite sink of electrons at zero potential. So that's first thing. It has zero potential. A potential of zero is a potential of 0 volts, and it was also an infinite source and sink of electrons. These are terms we use in environmental science. An infinite source, it's pretty self-explanatory. It means if I want to, I can pull an infinite number of electrons out of ground, okay? An infinite sink of electrons means I can push an infinite number of electrons into ground if I want to, okay? When we're dealing with circuits, this unit's about capacitors, but is very tied in with the circuits unit, so I'm going to discuss some preliminary topics for that unit. When we are discussing points that have a potential difference, like when we reference back our diagram of the potential equipotential lines from the previous video, let me try and put a picture of that up right here. You'll see that the equipotential lines are circular about the central charge, and there is a change in potential as you traverse some distance along the electric field lines, okay? Therefore, that means if there is a potential difference, there is a direction in which charges want to drift, okay? If there's a potential difference and I shove another positive charge in there, the positive charge will try and go from high potential to low potential. So whenever there is a potential difference, charges will flow. Whenever there is a potential difference, there necessarily must be an electric field. So if I have, let's say, a source of positive charges, okay? This isn't a real thing, but I'm just demonstrating for the purposes of your understanding. If I have a source of positive charges, and those positive charges are at a potential of 5 volts, and I were to connect those positive charges through a conductor to ground, like we discussed previously, ground is at a potential of 0 volts. Therefore, we have a potential difference here. Since we have a potential difference, we have an electric field. Since we have an electric field, charges are going to want to move. So charges will move from the source of positive charges to ground, okay? Now, it's important to understand what I mean when I say charges move, okay? On the first page of your reference table in the assumptions section, we say that, where is it? the direction of current is the direction in which positive charges would drift, okay? So we are saying that current flows from positive to negative because we are defining it as the direction in which positive charges would drift. I discussed previously that positive charges cannot move, only electrons can move. Therefore, what is really going on here is electrons are being pulled out of ground and flowing to the positive charge, okay? So now that we understand some basic concepts about potential difference and charge and electrons and current and all of this, let's get into the real topic of this unit, which is the capacitor, okay? So a capacitor relies on electrostatics for its operation, okay? So a capacitor is often drawn as two parallel plates, and those plates are separated from each other. The two plates are conducting plates, but they are not connected to each other, so they cannot conduct between them. Rather, one plate is connected to one side of a battery, while the other plate is connected to the other side of the battery. There are specific symbols that I should be drawing to represent the battery, but we're going to cover that in the circuits unit. Let's say this is the positive side of the battery, this is the negative side of the battery. Let's say this is a 5-volt battery. What does that mean? How is the capacitor going to work? Okay. What happens is, first of all, charges, positive charges, are going to drift out from this end. Now remember the technicality here. Positive charges don't actually move. When I say positive charges drift this way, what's actually happening is negative charges are drifting in the opposite direction. Just keep that technicality in mind. And on the right side of the battery, negative charges are going to be flowing in this direction, okay? Therefore, the left side, the left plate, is going to become positively charged. And the right side, the right plate, is going to become negatively charged. So I have positive charges and I have negative charges. Therefore, within the capacitor, there is a net electric field going from positive to negative. Okay? The positive charges are also exerting an electrostatic force onto the negative charges. So they are pulling each other together. Okay? So I can build up some charge on here. I can build up some charge Q on the capacitor, and then I can remove the battery from the circuit. Okay? At that point, when I remove the battery of the circuit, the charges can't go anywhere. The charges stay on the capacitor. Okay? Which means I have some amount of charge Q that is stored in the capacitor. There is some electric field between those two ends, and they are stored at some potential difference. Okay? Let's reanalyze what the potential difference means in this case. Potential difference, delta V, is often denoted as electromotive force. Now, electromotive force, the symbol is the capital epsilon, okay? So there's a reason for that. Electromotive force is interpreted in circuits, in capacitors, that is the force with which charges move through the circuit. So if we reconsider the fact when the battery is connected to the capacitor, positive charges are flowing to the positive plate, but as positive charges accumulate on the positive plate, they repel more positive charges, which means every positive charge that comes on is going to be harder to put onto that plate than the previous one, because the more positively charged the plate is, the more it will repel additional positive charges, and the same is true for the negative plate, okay? So that means that charge will continue to flow from the battery onto the capacitor until the voltage potential difference across the capacitor is equal to the voltage potential difference across the battery. Okay, we discussed previously that voltage always flows from charge always flows from high potential to low potential, meaning that at the beginning, our capacitor is charged with 0 volts because it has 0 charge, but as charge begins to accumulate on the capacitor, it develops an electric potential of its own, and it will continue to increase its electric potential until the potential is exactly balanced between the battery and the capacitor. And since electric potential is balanced, no current will flow. No charge will flow from one capacitor to the battery or from the battery to the capacitor. The equation on your reference table that describes this relationship is C, the capacitance of your capacitor, is equal to the charge it can hold divided by the potential difference applied to it. Okay, so what does that mean? If I were to take this battery out and replace it with a 9-volt battery, the 9-volt battery, being a higher potential now, would force a great deal more charge onto the capacitor. Okay, so a capacitor doesn't have a set constant capacity, rather it has a set constant capacity for a given potential difference applied across it. Means if I am only gently pushing charge into the capacitor, then it can only hold this much. But if I apply more electromotive force, if I apply a greater potential difference, then it can hold a great deal more. Okay? And that ratio between the charge the capacitor can hold divided by the potential difference, the electromotive force that you need to apply to it, is the capacitance. And the capacitance is a constant. It's like the mass of an object. It doesn't change. Another equation that we have to describe capacitance is C equals kappa epsilon naught area over distance. Okay? That's the next equation down on your reference table. So what specifically does this mean? Kappa is something we're going to discuss in just a few moments. We're going to keep that in the back of our heads right now. So let's only consider this section of the equation. Okay? Epsilon naught is a constant. It's the vacuum permittivity constant. So I want to rewrite this equation as the capacitance is proportional to the area over the distance. So in a parallel plate capacitor, again, these are plates. So if I turned this circuit 90 degrees and I looked at it from a different angle, this would look like a square to me, or some plate. Okay? So therefore, the capacitance is equal to the overlapping area. What do I mean by overlapping area? In the two plates, it's very common for you to have two plates that are the exact same size and shape. But in the off chance that you don't, in the off chance that you're given one plate that is bigger and one plate that is smaller, like a circle, the area in this equation is a reference to the overlapping area between the two plates. So in this case, the overlapping area would just be this pi r squared, the area of the circular plate. Okay? The distance is the separation, the distance between the two plates. Okay, so what does this equation tell us? It means that the larger the plate, the larger the capacitance. The larger the plate, the more charge the capacitor can store, which makes absolute sense. If I have more space, I can put more stuff there. The distance, as distance increases, the capacitance decreases. As the separation between the two plates increases, the amount of charge I can store on the plates decreases. Why is that? Because as distance increases, recall that I said there was an electric field from positive to negative here, okay? One of the main contributing factors to the point that the positive and negative charge can stay on this plate is because the positive charges are attracting the negative charges and vice versa, okay? It's because the electric field. If I separate the plates a greater distance, I would decrease the value of the electric field. If I decrease the electric field, these two charges feel less of an attraction to one another. So they're not going to want to stay on that plate. Okay? So that's the contribution of distance. Next equation we have is our potential energy stored in a capacitor, given by 1/2 times Q times the potential difference, which is analogous to our electric potential energy equation, which is just a charge Q times its potential. Okay? But we're focusing on this right now. we can rewrite this equation in a different form, say with this equation. We can say that our potential difference is equal to Q over C. So therefore this can be rewritten as 1/2 Q squared over C, or we can do Q and say that Q equals C delta V. So the potential energy stored in the capacitor can again be rewritten as 1/2 C delta V squared. So it's important to understand how you might be able to rewrite this equation in terms of what you're given in your problem. We're going to discuss the conservation of energy applications of this equation next unit in the circuits unit, probably my favorite unit. But until then, it's just important to understand this equation, okay? From there, we move on to the concept of dielectrics, which is the kappa, the Greek K that I told you not to worry about in this equation. Well, now we're going to worry about it, okay? What is a dielectric? A dielectric is a non-conducting material that I put in between my parallel plates, okay? So this is where the applications of charging stuff that we discovered in AP Physics 2, that's where this comes into play, okay? So let's say I'm connecting my capacitor to a battery, and I have positive charge accumulating on the left plate, negative charge accumulating on the right plate, okay? In the dielectric, the negative charge on the right plate is going to attract positive charges inside the dielectric. So positive charges are going to become present on this side of the dielectric. On the positive side, of course, is going to attract negative charges on the dielectric. Therefore, we can see here that the electric field created by the negative plate is satisfied by the electric field by the positive charges in the dielectric, okay? So the polarization of the dielectric acts to oppose the electric field created by the plates, okay? So if the electric field created by the plates goes from positive to negative, the electric field inside the dielectric also goes from positive to negative. They oppose each other, okay? Therefore, if the electric fields oppose each other, the electric field created by the plates has a much larger proclivity to increase the magnitude of the electric field, okay? Because the electric field can sequester much more charge this way. If I have a negative charge is really unhappy when it's alone. Negative charge wants to be as close as possible to positive charge, and the dielectric constant helps it do that. Therefore, any dielectric will increase the capacitance of your capacitor. It makes the charges on each plate more stable. So therefore, more charges can be accommodated on any given plate. So that is why your dielectric constant is in the numerator of your capacitance equation. The higher the dielectric constant, the more polarizable your dielectric. You know, the more polarizable it is, the greater its ability to mitigate the repulsive forces, the greater its ability to keep the negative and positive charges happy, keep them stable, okay? So the dielectric constant, kappa, as you might assume, is a constant. It's a constant that's characteristic of the material. I can't remember if I mentioned, but I'll just say it again. The dielectric is an insulator. It's not a conductor. If it were a conductor, then negative charge would just flow to positive charge. It's an insulator, okay? Another equation you have on your equation sheet is the equation of the dielectric constant, kappa, equals epsilon over epsilon naught. Now, this requires an understanding of what exactly epsilon naught is, okay? Epsilon naught is vacuum permittivity, is the permittivity of free space. So what does that mean? It means permittivity is how easy or how much electric field can permeate a material, okay? So the permittivity of free space is basically saying how much electric field is free to permeate or free to move throughout a vacuum, okay? So E naught is vacuum permittivity, and E is going to be the permittivity or permittivity of our dielectric, okay? It's a measure of how polarizable, how easy electric field can move and stabilize through the material, okay? So in the context of that, the dielectric constant makes sense in terms of its application. Okay. Are there any more equations we need to go over? Nope. Thanks for watching, guys.